Generating power at utility scale requires an immense physical footprint. Across the globe, multi-megawatt solar farms span thousands of acres, forming endless geometric grids of glass and silicon. These sprawling energy fields are constantly evolving. Every single day, environmental stress, extreme temperatures, and operational wear quietly degrade individual panels across the grid. Historically, maintenance crews found these faults through manual labor. This required walking miles of uneven terrain, physically climbing support structures, and eyeballing thousands of modules one by one. Attempting to spot a single malfunctioning module across a utility-scale installation is a massive logistical hurdle. The process is slower and far more hazardous than searching for a needle in a haystack. Even when a crew can check every inch of a facility, human vision has physical limits. We can only spot surface-level issues like shattered glass, bird droppings, or heavy dust accumulation. Relying solely on human sight leaves the most destructive internal electrical failures completely hidden until the system's power output drops. To solve this, operators now deploy industrial-grade inspection drones like the DJI Matrice 4T. These automated diagnostic platforms turn high-altitude flights into precise technical assessments of the plant's health. Capturing accurate diagnostic data requires strict environmental conditions. You need low wind, clear skies, and a midday solar window to ensure stable sunlight before the drone gets off the ground. Once airborne, the drone deploys its first payload, a high-resolution RGB sensor. This operates as a vastly upgraded, airborne version of the human eye. Looking down from above, the RGB sensor maps out the exact locations of dirt accumulation, tracks shadows cast by encroaching trees, and records microscopic physical fractures across the glass surface. The RGB sensor drastically accelerates the inspection process and keeps human crews safely on the ground, but it remains limited to documenting the physical wear and tear visible on the surface. Finding internal threats requires a second payload, a radiometric thermal camera. This shifts the inspection into the invisible realm of heat. When a solar cell suffers an internal defect, it stops converting sunlight into electricity. Instead, that trapped energy immediately converts into heat. In a healthy solar cell, sunlight hits the top layer, converting into a forward-moving, linear flow of electrical energy. But if the cell suffers from delamination or a manufacturing microcrack, that flow hits a wall. The energy stalls, creating a localized hotspot that radiates outward. These isolated hotspots are early warnings for systemic threats like PID, or potential induced degradation, where high-voltage stress degrades performance across an entire array. This simplified string of connected panels glows with a uniform, healthy temperature gradient. Systemic issues like PID create cascading power losses. The drone's advanced sensors read absolute temperatures to detect these specific cascading heat patterns, diagnosing complex electrical issues from the air. This thermal data effectively makes silent, invisible electrical degradation glaringly obvious to maintenance teams. The true work begins after the drone lands. The flight leaves operators with thousands of disconnected dual-spectrum images that require synthesis. Individual files are digitally stitched together to construct a massive, highly accurate thermal map, called an orthomosaic, of the entire plant. This digital wireframe represents the solar farm's layout. Automated software analyzes the thermal map to pinpoint every defect. The system categorizes these faults, assigning strict priority levels, separating minor dust buildup from critical diode failures needing immediate attention. A diagnostic process that once required weeks of dangerous guesswork now generates a precise, geotagged hit list for maintenance teams in just 1 to 3 days. Dual-spectrum drone inspections provide the essential diagnostic data required to protect the efficiency, safety, and lifespan of our solar infrastructure.